Okay. Okay, hi everyone. So, yeah, great. Hi. So, let's continue where we stopped. So, last session, we covered introduction to the course and some of the preliminaries. We came until here, eigenvalue and singular value decomposition. So, let's go over this a bit. And then after this preliminaries, we'll go to one neuron only. We start with one neuron. So what is eigenvalue and eigenvector in the space? By the way, this small part is shared between two courses. If you have both courses, I apologize for repetition. But so, for example, in a statistical machine learning course, in addition to this part, I also cover some optimization problems which yield to eigenvalue problems. But for deep learning, that's not required. But eigenvalue problem is required for deep learning because we have eigenvalue decomposition in deep learning. You might be wondering how we have. For example, in graph neural networks, we have. Okay, when we have a matrix, by the way, you know what is matrix decomposition? Also called matrix factorization. So what is that? So when you have a matrix, you can write it as a multiplication of several matrices. This is called matrix factorization or matrix decomposition. Usually, we decompose a matrix into 2 to 3 matrices, usually. And there are different algorithms for matrix factorization in linear algebra. For example, one of them is Cholesky decomposition, right? One of them, which is very famous, is eigenvalue decomposition. The other one is singular value decomposition. So eigenvalue decomposition and singular value decomposition are two most well-known and used decompositions in machine learning. So here, what is eigenvalue and eigenvector? When we have a matrix, this matrix usually has some directions in the space. Okay, you find some informative directions in the space. Those informative directions, we can call them eigenvectors of that matrix. And what are the eigenvalues? The amount of importance, the amount of information along those directions are the eigenvalues. So an example, consider covariance matrix. So what do the eigenvectors of the covariance matrix tell me? What is the information of covariance matrix? Metric. So yeah, for eigenvalue decomposition, the matrix must be symmetric and also square. Must be square. It must not be symmetric, I believe. But if it is symmetric, it has some properties. But yeah, covariance matrix is a square and symmetric, so it's suitable for using eigenvalue decomposition on that. But I'm saying that what are the information in an eigenvalue in the covariance matrix? Variance, exactly, right? So therefore, its important directions are the variance directions of the data, where the data is spread, right? For example, consider this cloud of 2D data points. Then this direction has the most variance, right? The next direction which has the most variance is this, right? And the eigenvalues will show how much variance do I have along that direction. For example, along this direction, I have more variance than along this direction, right? So these are the eigenvectors of covariance matrix of this cloud of points. Also, the eigenvalues show the amount of variance. So yeah, this is the intuition of eigenvectors and eigenvalues. And it has been used a lot. It has usefulness in various fields of science, including physics, mathematics, I don't know if you have heard of Poincare conjecture. Have you heard of that? It was proved several years ago, about 15 years ago, I guess, by Grigory Perelman, a Russian mathematician. He was a genius. He proved that it was unsolved and unproved for a century. Finally, he proved that, and in his proof, he has used eigenvectors and eigenvalues. And so I'm saying that it's very important in all fields of science. Okay, so in the eigenvalue problem, the eigenvectors, as I said, of matrix represent the most important and informative directions of that matrix. And these directions are, if we can also impact these directions by another matrix. If we do that, then we'll have generalized eigenvalue problem. Okay, we'll see both. We'll see both eigenvalue and generalized eigenvalue problems. So the eigenvalue problem of a symmetric matrix A, D by D, it must be a square matrix, is defined as this. A phi I equals lambda I phi I for I from 1 to D. Okay, so I have D eigenvectors which are phi i's, right? Phi i's are the vectors. These are D-dimensional, D by 1 dimensional. And also D eigenvalues, which are scalars, 1 by 1 scalars. So I have D eigenvalues as well. If I write them in matrix form, then I will have this A phi equals phi lambda, where I'm stacking the eigenvectors column-wise to have the matrix phi. Therefore, phi becomes D by D, because I have D eigenvectors, each of which is D-dimensional, right? And I can also put the eigenvalues as diagonal elements of a diagonal matrix, and I call that the matrix lambda. Therefore, the matrix lambda is also D by D, right? Okay. And yeah, as I said, eigenvectors are D-dimensional and eigenvalues are scalar. Why? Because my matrix is D by D. The matrix can be non-symmetric. If the matrix is symmetric, its eigenvectors become orthogonal or orthonormal, right? And if it is non-symmetric, then its eigenvectors are not necessarily orthogonal or orthonormal. What is orthonormal? When I say two vectors are orthogonal, it means that they are perpendicular to each other, right? Their inner product is 0, right? What is orthonormality? When I say two vectors are orthonormal to each other, what does it mean? In addition to being orthogonal, which is perpendicular to each other, their length is also unit, right? They have unit length. And what do I mean by unit length? It means that the L2 norm of the vector is 1. And when, by the way, what is an orthogonal matrix? So if in a matrix A, for example, the columns are orthonormal, then this matrix becomes orthogonal matrix. They don't call it orthonormal matrix. They call it orthogonal matrix. Okay. So when the matrix is symmetric, then its eigenvectors become orthonormal. Therefore, its eigenvector matrix phi becomes orthogonal. So you should note that for eigenvalue decomposition, the matrix must be symmetric, it must be square, but it can or cannot be, may or may not be symmetric. So consider this now. What was that? I just introduced that. This is eigenvalue decomposition, eigenvalue problem, right? Now, right multiply the sides of this equation by phi transpose, okay? Then what happens? Then I have A phi transpose equals phi lambda phi transpose. Do you agree? Then phi transpose becomes identity. Do you know why? Let me tell you a bit. I need to tell one note here. Let me add a page. Okay, so consider a matrix phi. A general matrix, okay. Let me call it B so you don't confuse it with the matrix of eigenvectors, the matrix B. B inverse B is always identity. Okay. But is B inverse identity? Not always, not always. This is happening when B is not rectangular. Okay. In other words, that is when it is not truncated. What do I mean by not truncated? I have several this is matrix P, right? It has its columns. If I get rid of some of its columns, so it's, for example, D by D. If I make it D by P, so where P is less than D, then it means that the matrix has been truncated. Okay. Then if I truncate that, B inverse is not identity. If I don't truncate that, then B inverse is also identity. Okay. So now consider an orthogonal matrix. Assume B is orthogonal matrix. According to linear algebra, one of the properties of an orthogonal matrix is that B transpose equals B inverse. Okay. Then, in this case, what happens to B transpose B? According to this property, it is B inverse B, so it's identity, right? What happens to B transpose? It's B inverse, and there is an if here. If we don't truncate that, it means that if all of its orthonormal columns are available, then that becomes identity. Okay, that's clear. So that's one thing I wanted to let you know. Now, let's go back to where we were. So we have A phi transpose equals phi lambda phi transpose. This, as phi is an orthogonal matrix according to the properties of eigenvalue problem. Okay, in eigenvalue decomposition, the matrix of eigenvectors is always orthogonal. So it's equal to phi inverse. And as I haven't truncated the matrix phi, this is identity, right? Is it clear now? Okay, so now I have A equals phi lambda phi transpose, which is equivalent to phi lambda phi inverse. Why? Because phi is an orthogonal matrix. What is this? In the literature, they call it eigenvalue decomposition. So they call this eigenvalue problem, this eigenvalue decomposition. Also, they call this a spectral decomposition. Eigenvalue decomposition, eigen decomposition, different names for the same thing, right? That's why I don't know if you have heard of spectral methods in machine learning. For example, PCA is one of the spectral methods in machine learning. Why do they call them spectral? Because they usually reduce to an eigenvalue decomposition or eigenvalue problem. Okay, when you solve their optimization problem, they usually have some eigenvalue decomposition in them. That's the reason. Okay. Now, generalized eigenvalue problem. Consider two symmetric matrices A and B. They are both square D by D. Then I can have A phi I equals lambda I, B phi I. As you see, I have B here now. Then we call this generalized eigenvalue problem. In matrix form, if I put the eigenvectors and eigenvalues in matrices, then I will have A phi equals B phi lambda, where phi has the eigenvectors and lambda has the eigenvalues in its diagonal. As you see, obviously, eigenvalue problem is a special case of generalized eigenvalue problem if we set B to identity, right? Okay. This A, so in parentheses A and B, is called a pair or pencil. So phi and lambda are called the generalized eigenvectors and eigenvalues of A and B. The phi and lambda are also called eigenpair for the pair A and B. Okay. in machine learning, you see this a lot. You see this generalized eigenvalue problem a lot. By the way, although there is algorithm for solving, iterative algorithm for solving this and finding the eigenvectors and eigenvalues, you can simply make it an eigenvalue problem. How? Can you give your guesses? Assume I have equation 10, which is a phi equals b phi lambda. Can I make it similar to a phi equals phi lambda, which is the eigenvalue problem? I mean, in this form, can I make it? So I have a phi equals b phi lambda. What happens if I left multiply? So this is a pain in the neck, right? Whenever you have a pain in the neck in linear algebra, you try to multiply it by its inverse, right? So get rid of that. Therefore, let me left multiply the sides by b inverse. It's important whether we left multiply or right multiply because we have matrices now. Okay, so it becomes b inverse a phi equals phi lambda. Now call this b inverse a matrix C. This becomes C phi equals phi lambda. Therefore, phi and lambda are the eigenvectors and eigenvalues of the matrix C. What is this? This is an eigenvalue problem, although this was a generalized eigenvalue problem. You see the beauty. Okay, but in addition to seeing the beauty, there is a big problem here. Can you see the problem of this beauty? Is everything fine mathematically? B inverse, okay, so when B equals to I, that's fine. Then I inverse is I, right? But B inverse is a problem, actually. What is the problem? What if B
is not a
no, if is not invertible? What is it is not invertible? In other words, what if B is singular matrix? What does a singular matrix mean? It means that at least one of its eigenvalues is 0, okay? When you have 0 eigenvalue, then what happens? The matrix, you can't inverse it. Then what can I do to solve that issue? Give me your answers. If it's wrong, that's fine. Let it be discussion based. So I assume if B is invertible, none of its eigenvalues are 0, then the world is easy. We can take B inverse, okay? But what if B is singular matrix? I think, have you coded in MATLAB or Python? You see a lot of these warnings and errors. If it is singular, it will give you error. If it is close to singular, it will give you warning. If you have coded MATLAB, you see a lot of orange warnings saying that your matrix is close to singular. What can I do? So there are at least two things that I can do. Okay, one thing is that I take the pseudo inverse. Okay, pseudo inverse tries to approximate the inverse. Okay, you can Google it. That's not a hard thing. Okay. Another way to handle that is that rather than B inverse, let me open a page. By the way, if I remember the pseudo inverse, let me A phi equals B phi lambda. Let me think. Hopefully I can remember. Let me Google it because I usually can't memorize things. That's why the exam is open book. Yeah, just give me a sec. I believe memorization is not important. Understanding is important. Okay, so we have various ways to do pseudo inverse, but yeah, one of them is this. So A phi equals B phi lambda, right? So what can I do? Let me tell you about the pseudo inverse. I believe when you learn these, linear algebra becomes sweet for you. So what is that? Yes, speech. Okay. Assume. Yes, I think I'm right. Left multiply the sides by B transpose. I will tell you why. Then this is a pain in the neck, right? The pain in the neck became B transpose B. So what should I do? Multiply by its inverse, right? Therefore, I will say B transpose B inverse B transpose A phi equals phi lambda. Now I call this C, right? This became the eigenvalue problem of B transpose B inverse B transpose A, correct? We call this pseudo inverse of B. Rather than B inverse, they usually write it as B dagger or B cross. Cross is dagger in math, okay? B cross or B dagger. Then this is called pseudo inverse. And what is the philosophy of this B transpose? What does it do? Assume B is singular. Then B transpose B is not singular. You make it non-singular, and then you inverse it. You see that. By the way, we have two types of pseudo inverses based on whether it's a horizontally rectangular or vertically rectangular. Okay, doesn't matter. So you can Google pseudo inverse or Moore. Its full name is Moore Penrose inverse. Pseudo inverse. Okay, you can see it's Wikipedia. Doesn't matter. So that was a pseudo inverse. But now let's go to the other technique that I told you, B phi lambda. This is used a lot in machine learning. Okay. That, as I said, B inverse A phi is phi lambda, but this is a problem. What if it's singular? We do a hack. We are lazy. We don't do the pseudo inverse, but we do a hack. B plus lambda inverse A phi equals phi lambda. What does lambda is a small positive number, such as 0.01. Okay. I is identity matrix. What am I doing here? Rather than having B inverse, I'm having B plus lambda I inverse. What does plus lambda I do? So lambda I, what is that? It's that diagonal matrix with lambda on its diagonal, right? Then I have B plus this. What does it do? It adds lambda to the main diagonal of B, and then I inverse it. In other words, I'm strengthening the main diagonal of B. What does it do in linear algebra? When I strengthen the main diagonal of a matrix, it becomes full rank. When it becomes full rank, it becomes invertible. By the way, these are all opposite of each other, being singular and being full rank. When you are not full rank, you become singular and you're not invertible, okay? So by this hack, I'm strengthening the main diagonal, so it becomes full rank, so it becomes invertible. Now I won't get the warnings of MATLAB or Python. However, there's another problem which occurs. Have you heard of this proverb? You want to correct its eyebrow, but you make it blind, something like that. So there's a problem here. Is that now I have adding some inaccuracy by adding this lambda I. So you're sacrificing your accuracy for making it invertible. Okay. Therefore, the larger the lambda, the less accurate I am, but the more full rank I am. The less the lambda, the more accurate I am, but the less invertible I am. So there's a trade-off. So you try lambda to be as small as possible, but not too small that it becomes singular. Okay, so that's the thing. And this hack is used a lot. Okay, So I think we talked about this a lot. And I think just in parentheses, this is not related to this course. If you have heard of Fisher discriminant analysis in machine learning, that's related to statistical machine learning. We have, I think I'm right. Yes. So SW is the within scatter of the classes, and SB is the between scatter of the classes. So we have this. This is exactly a generalized eigenvalue problem. They do this SW inverse SB phi equals phi lambda using this technique that I told you. And I think you have seen this a lot in machine learning. SW inverse SB, that's exactly where it came from. But they also add in Fisher discriminant analysis, they say, what if SW is not invertible? Then they do this hack exactly. Okay. So let's continue with deep learning. Now, singular value decomposition. SVD is also very important in machine learning and deep learning, and because it's kind of related to eigenvalue decomposition. Okay, so singular value decomposition is another matrix decomposition methods. It can be solved using different algorithms such as Jordan's algorithm. Here in this course, as you see, I never covered how to find the eigenvectors and eigenvalues, or how to find the singular vectors and singular values. I assume you can use libraries, right, for that. That's out of the scope of this course. That's in linear algebra. We are going to use them, right? And analyze them. So SVD can be applied on rectangular matrix. Therefore, so in eigenvalue decomposition, the matrix must be a square. But here it can be rectangular, alpha by beta. So I have U sigma V transpose. And I have two types of SVD, either complete SVD or incomplete SVD. So let's talk about complete SVD. By the way, in both complete and incomplete SVD, U is called the matrix of left singular vectors. V is the matrix of right singular vectors, right? Because it appears right. And sigma is the matrix of singular values. Okay. Why didn't I have left and right eigenvectors in eigenvalue problem? Because the matrix was square. So I had U sigma U transpose. In both sides, I had U in left and right. Here I had U sigma V transpose. U and V are different because this is a rectangular matrix, right? In fact, if you make this matrix a square, U and V become similar. Okay. So now, in the complete SVD, U becomes alpha by alpha, V becomes beta by beta, and sigma becomes alpha by beta. Therefore, U and V are square matrices, but sigma is a rectangular matrix. However, sigma is diagonal rectangular matrix. You might have not heard of that, but now you see that. So this is diagonal rectangular matrix. It means that either I have these elements and the rest as 0, or I have these elements and the rest of 0, based on whether alpha is less than beta or greater than beta, right? Okay. And we have U and V also. So, but in the incomplete SVD, U and V are rectangular matrices, and sigma is a square matrix, a square diagonal matrix. K by K, U becomes alpha by K, and V becomes beta by K, where K is usually minimum of alpha and beta. Yes. Now, U, according to the properties of the SVD, U and V are both orthogonal matrices. Okay, so their columns are orthonormal. Right? Note that when I say their columns are orthonormal, so this is V transpose. I'm talking about V. So the columns of V are orthonormal. Therefore, the rows of V transpose are orthonormal. Okay, so that's one thing. Therefore, according to linear algebra, what is U transpose U? It becomes U inverse U. So it's identity. What is V transpose V? As it is orthogonal matrix, it becomes V inverse V. So it is identity. What about U transpose? if I don't truncate it, if I keep all of the left singular vectors, then U transpose becomes identity. But if I truncate that, it's not an identity anymore. What about VV transpose? If I don't truncate it, if I have all of the left singular, right singular vectors, then it becomes identity as well. Okay. Now, relation of SVD and EVD. As I told you, there is a relation between eigenvalue decomposition and singular value decomposition, and we'll see that. So here it is. In both complete and incomplete SVD of A, the left and right singular vectors of the so the left and right singular vectors are the eigenvectors of A transpose and A transpose A respectively. In other words, the left singular vectors of A are equivalent to the eigenvectors of A transpose. The right singular vectors of A are equivalent to the eigenvectors of A transpose A. And the singular values are the square root of eigenvalues of either A transpose or A transpose A. Now let's see the proof. Okay. So let's start with A transpose. Let me replace A with its singular value decomposition. Right. Therefore, I can say U sigma V transpose times U sigma V transpose transpose. Right. Again, according to linear algebra, A plus B transpose becomes A transpose plus B transpose. We see that a lot in machine learning. Okay. And also, what about AB transpose? Yeah, exactly. It reverses the order. B transpose, A transpose. So it reverses the order. Okay. So let's see that. Therefore, this reverses its order. So it becomes V sigma transpose equals sigma because it's diagonal. U transpose, right? Interestingly, I have V transpose V in the middle, which is identity because V is an orthogonal matrix. So I will have U sigma sigma U transpose. Sigma sigma is sigma squared, right? Therefore, I have U sigma squared U transpose. And so we started with this. Consider this left-hand side equal right-hand side. What is that? A transpose equals U sigma squared U transpose. What is that? We just saw that a few minutes ago. What is U? Consider this sigma squared as lambda, whatever. U lambda U transpose with what? It's exactly eigenvalue decomposition. So it's the eigenvalue decomposition of A transpose. However, so on the one hand, we saw that U is the eigenvectors of A transpose, and sigma squared are the eigenvalues of A transpose. On the other hand, we know that U was the left singular vectors of A, and sigma was the singular values of A. So comparing these two sentences, you will get exactly what we have in. Let's see the other one. A transpose A. Again, replace A with its singular value decomposition. Then this transpose reverses the order. Interestingly, I have U transpose U in the middle, which is identity because U is an orthogonal matrix. Then I have V sigma sigma V transpose. Then I have V sigma squared V transpose. Therefore, on the one hand, V is the eigenvectors of A transpose A. Sigma squared are the eigenvalues of A transpose A. On the other hand, we knew that V was the right singular vectors of A, and sigma was the singular value of A. So comparing these two sentences again, you will get what we have. Right? Interesting. Some acknowledgement, some slides are based on our textbook, Elements of Dimensionality Reduction and Manifold Learning. And for more information on optimization, you can refer to my optimization course available on YouTube. So these are the references. Okay. Any question before we continue? Yeah.
Decomposition are necessarily related to machine learning tasks. Is that because in machine learning tasks, I mean, the optimizer, like Adam, using this kind of optimization problem?
So usually the optimization problems that so there are some. So the question is, why is eigenvalue decomposition important to machine learning? So there are at least several ways to answer this question, I believe. So first off, we have a lot of optimization problems which simplify to an eigenvalue problem. It's out of the scope of this course. For more information, see the lecture in the statistical machine learning course available on YouTube. Okay. So we have some optimization problems. When you solve them, at the end, you will end up with an eigenvalue problem or generalized eigenvalue problem. This is one reason. Another reason is that, according to the intuition that I said, so eigenvalue problem shows us the important directions of the matrix. And usually we want to find important information or important directions of the matrices in data analysis and also machine learning. That's the reason. Okay. Any other question? No? So let's continue with one neuron. So let's start with training one neuron. Okay. So neuron and the McCloch-Pitts model. By the way, many deep learning courses do not cover these things because these are the history of deep learning. They might say these are not useful, but I believe it's good to know the history of neural networks too. So, for example, if you had passed a course about neural networks in the year 2000, these were actually the main concepts of those courses, right? So if you take a look at, I think at the end I have acknowledged that book. If you take a look at one of the books, for example, published in 1995 or 2000, there are about, I think, 500 pages about these things, right? Different variants of training very simple neural networks. And we will see in this lecture series that, for example, they worked, I think, about 30 years in the Stanford University and just these simple neural networks. And nowadays, those are outdated, but we will review them. That's why I try to start from the fundamentals. So neuron and the McCloch-Pitts model. Biological neuron, so nucleus. The nucleus is the neuron cell. So we have neurons are the fundamental parts of our brain, right? And the neuron cell is called nucleus. And we have, so here, for example, in this figure, this is the nucleus, right? The cell of the neuron. And we have soma. Soma is the cell body of the neuron containing the nucleus. So this is the nucleus, and soma contains the nucleus in the cell. We have dendrites, which is these branches. So these branches are called dendrites. So usually the dendrites of one neuron become close to the dendrites of another neuron, such as exactly how my fingers are. But they might not be exactly connected to each other. There might be some liquid or something between them. And then the electrical signals, electromagnetic signals, whatever we call them, comes from one of them and is transferred to the other one. Okay. So as I said, we have some synapse or gap between the dendrites, and then the information comes and maybe jumps to here, okay, and enters the next neuron. So we have a small gap between the dendrites. Okay, this is how a biological neuron works. Then in 1943, the first model of the neuron was invented by McCloch, who was a psychologist, and Pitts, who was a logician. So in 1943, two people, one of them from physiology and biology, came to the other person, which was a logician, said, let's propose artificial intelligence. Okay, so therefore it was later named McCloch-Pitts model. The model had two inputs, and a single output. Okay. So a neuron, they would not activate, this is their justification, would not activate if only one of the inputs was active. So they said, let's have a model which has two inputs. If both inputs are active, then the output becomes active, right? As you see, this is related to logic, right? So, and they also had weights for each input were equal and fixed. So at that time, initially, it was fixed. They were not learning them. And the output was binary, 0 or 1, because of logic. Until inputs summed up to a certain threshold level, okay, output would remain 0. After some threshold, the output would become 1. They were inspired by biological neuron. Okay, biological neuron is also working with some thresholds. In other words, that after that threshold, the neuron is fired. Okay, this model is known nowadays as a logical gate, such as and or not. So now I think you can also see the history of logical gates as well. So formula is this. So output equals f of summation of wj xj plus w0 for all d dimensions. Here, I'm assuming I have d dimensions, okay? So d features. Therefore, I have x1 to xd. And for each of them, I have some weights. So I have w1 to wd. Then I can multiply them to each other. So what is this, by the way? This is the inner product between the vector of weights and the vector of data, right? Plus w0 for y, for having the bias, exact. By the way, when I have A transpose X, or in a scalar form AX, this is a linear function, right? But what if I have plus bias? What is this? They call this a affine function. In the literature, usually people call this also linear function, but it's inaccurate. Mathematically speaking, this is not a linear function. This is an affine function. Okay, but people, they say, okay, let's call this linear as well. Okay, when you have bias, if you want to be accurate, that's a affine function. So you have a affine function here. We can kind of absorb this W0 inside this summation. How? If we assume we have x0 and we set it to 1, right? Or you set it to some constant, because if you set it to 2, then W0 will be learned to be W0 over 2 to cancel that 2, right? Doesn't matter. So you have summation of, now this summation starts from 0, j from 0 to d wj xj. Then what is this f? We call it activation function. So we sum them and then we feed that to the some function called activation function. The activation function in the McCloud-Pitts model is a binary function. Okay. By the way, these initial slides might be easy and boring, but I try to go fast over them so you don't get bored. But I believe if you understand these, then you will understand the fundamentals of neural network. So I have this summation w1 x1 until wd xd, and then I have w0 x0 equals 1 for bias, and the output is O. Okay. So this is linear. This is linear. No. This is linear function with different slopes. This is a affine function with different slopes. A affine function has some intercept or bias. Okay. But in the literature, they sometimes called a affine function linear. Doesn't matter. Okay. So, by the way, from these easy parts, I'll also put some questions on the exam, so you get mark. Okay. You get. So now we covered McCloud-Pitts. Now let's cover perceptron. I think you have heard of this a lot, multilayer perceptron. So these are the fundamentals of nowadays deep learning. For perceptron, you should first know Hebbian learning. Hebbian theory is a neurophysiological theory claiming that an increase in synaptic efficacy arises from a presynaptic cells repeated and persistent stimulation of a postsynaptic cell. Forget these hard sentence. What does it mean? The more you repeat, the better you learn. Okay.
The basis of the muscle memory.
Exactly. So the more you repeat things, the more that pattern is repeated, the more that pattern stabilizes in your mind, in your brain. Okay. That's why when you start playing piano, initially you might not be good, but when you practice every day and every day, you get better in playing piano. That's exactly how it works. So Hebbian is named after Hebb, and he was a very famous biologist, I believe. I'm not sure whether he won the Nobel Prize, but I think he was close to winning Nobel Prize, or he won, I'm not sure. So in simple words, the more two adjacent neurons are activated or fired together, the stronger the connection becomes between them, right? Okay, so Hebbian learning, it was proposed by, yes, Donald Hebb in his 1949 book, The Organization of Behavior. So this is a very important book. At that time, it was a book. Okay, Donald Hebb. So Perceptron tried to learn by neuron as done in brain. Okay, he said, let's mimic what we have in our brain. Perceptron is the building block of nowadays neural networks. That's why we call them multi-layer perceptron. By the way, we'll see that Perceptron and ADALINE, they were competitors of each other from two different universities. And finally, Perceptron won. That's why nowadays, because neural networks, the building blocks of neural networks are Perceptron. If ADALINE had won, we would probably call them multi-layer ADALINE. Okay? Or they called it MADALINE. We'll see that. So it was a competition. 30 years of competition. Finally, Perceptron won. Okay. Perceptron was implemented by Rosenblatt, physiologist, in 1958 at Cornell Aeronautical Laboratory. So Perceptron was developed in Cornell University. Okay. I believe ADALINE was developed in Stanford University. So finally, in deep learning, Cornell won over Stanford. Okay. So it was for binary classification at that time, Perceptron, for binary classification. It was useful because what? Binary logic, so because logic was binary, right? Binary logic could do computer operations. And also, even when we have multiple classes, we can consider pairs of classes, right? Assume you have 3 classes. Then you have, how many pairs do you have? You can consider 3. So assume these class 1, class 2, class 3. I can consider these 2 as binary classes, these 2 as binary classes, and these 2 as binary classes, right? So you can make multi-class classification into several binary classification problems. And Rosenblatt randomly, at that time, initially, randomly connected perceptrons and changed the weights in order to achieve learning. So at that time, it was initial start of artificial intelligence. So he tried randomly initially. In later attempts, Hebbian learning was used for learning a perceptron. So they adopted the idea of Hebb, right? So in 1958, press conference organized by the US Navy, okay, Rosenblatt gave a speech. It was an exciting speech for them. With so much excitement, he said that it talked about perceptron. Afterwards, New York Times reported that the perceptron, it said, the embryo of an electronic computer that the Navy expects will be able to walk, talk, see, write, reproduce itself, and be conscious of its existence. At that time, they thought that they have solved artificial intelligence. When is artificial intelligence done and all of us will be unemployed? When does that happen? The moment that an AI can make another AI consciously. the moment that a machine learning algorithm consciously makes another machine learning algorithm to do something, then that machine learning algorithm can consciously make another machine learning algorithm, and this goes forever. Right? At that moment, the AI is over. It is finished. At that time, so this is exactly what they said. It can talk, walk, see, write, reproduce itself, make another AI, and be conscious of its existence. Right? Then they thought that they have solved AI just by using Perceptron. So they are very optimistic. They thought that they have solved AI. So now let's go into the mathematics of the Hebbian learning in Perceptron. This is the Perceptron, the figure. As you see, I have x1 to xt, w1 to wd as the weights, also w0 and x0 equals 1 for bias, right? Now I sum them up, and then I feed them to some activation function, here binary. The output, I call it O, right? Then I get the output, I compare it with some label. Now in Perceptron, I have some label, right? I compare it with some label. So label minus the output, then I feed it to the Hebbian learning. And what does this arrow mean? It means let's tune the weights. Okay. So you can see it as this: Wj equals Wj plus eta. What? Where is this yi minus oi? Because of this label minus the output times xij times some eta. What is this eta? This is learning rate, right? So this is a hyperparameter. You can tune it, and you do this for all j from 1 to d and for all I from 1 to n. So I denotes the data point, the data instance, and j denotes the dimensionality. So xij means the jth dimension of xi point, right? Xi is the dimensional vector, right? Here, as you see, I have n data points, so I have a data set for training. Okay. And also when for the bias, I have this, or you can assume that xi0 is 1 as a number. Okay. So eta is the learning rate, is positive. It must be positive. Why? Because if it is negative, then it does the opposite exactly the opposite of what we want. For example, minimize f of x. If you say minimize minus f of x, it becomes maximize f of x, right? So it does the opposite. And I have xi, as I said, the I input data. Yi is its label, right? So I have y1 to yn, and yi is a scalar here. Oi is the corresponding output of the perceptron for that input data. And as I said, if you consider xi0 to be 1, then you can combine these two equations to one thing. Okay. If we have batches, so in the previous slide, I was feeding xi one by one, x1, then x2, for example, right? Now here I can have batches of data, for example, x1 to x10. I feed them in one shot to the perceptron. And then in the next iteration, I go from x10 to x20, for example. Okay, so I have batches, and so therefore I have summation over the batch, right? B is the batch size. Okay, now let's interpret this. Okay. These formulas are not important. The interpretation is important. Let's interpret. So consider this that we had. When the output OI is the same as the target YI, what happens? It means that it is exactly what we wanted, right? We want OI to be exactly the same as YI, right? So when it is exactly equal, it's our desired thing, and actually this term, that updating term, becomes 0, right? Therefore, OI becomes, so WJ becomes the previous WJ. It's not changed, right? Interesting. So that is the interpretation of this formula. Although it's simple, right? We are making it more and more complicated in the other slides. Okay. Now, what if the activation function is a sign rather than binary? So rather than 0 and 1, we have -1 and 1 here. Okay, so between -1 and 1, okay, rather than 0 and 1. They also call it signum function. By the way, why in machine learning do we use -1 and 1 rather than 0 and 1, especially in statistical machine learning? For example, when you are working with SVM and these things. If you don't know what SVM is, that's fine. Just in classification algorithms, many of the times when we have two classes, rather than saying the labels to be 0 and 1, we use them as -1 and 1. What is the reason? Can you guess? No.
One is the desired output and the other is the, so it is, it has to do with like something that, if it's one, we can assign it that that is the desired entity that we require from the model. But if it's, it shows -1, so it can be interpreted as something that it is a wrong classification that is given by the model. So to penalize the
Yeah,
outcome.
but when we have 0 and 1, assume for 0 you say 1, or for 1 you say 0, then still you have some error. So for having error, 0 and 1 also work. The reason is this, that sometimes we use the label in the formulation of the problem itself. For example, in SVM, when we formulate the problem, we say that we want the distance, for example, to be always positive, some distance. Assume the distance of this point from this line, okay? This D, do you agree that might become negative if the point is below the line? What if I want this to always be positive? Then I can simply multiply it by its label. If Y is positive and D is positive, Y times D is positive. If D is negative, Y is also negative, -1. So YD is always positive. In this way, I can unify the two cases into one case, YD, all right? But if I have only 0 and 1, I can't do that. I can't do this trick because I have -1 and 1. Because of these tricks, these are small tricks you usually see in machine learning, you use -1 and 1 rather than 0 and 1, okay? So maybe they had these ideas when they were developing these algorithms. Just this was in parentheses, okay? So sign or signal function, when we have the formula becomes this. Wj equals Wj plus 2 eta yi xij if oi is not equal to yi. Otherwise, you don't change that. You don't change. Otherwise, when this is exactly the desired thing, right? Then you don't change. Sorry. Okay. You do this for all the features and all the data points. And for W0, your xij is 1, right? So it's simplified in this way. What?
Why is it 2 eta y?
We will see. We will see. I'm gonna prove these things and interpret. So we will not leave anything without interpretation. We'll talk about. So, by the way, we can write it in this way. Right. We can restate or rewrite equation 5 and 6 as equation 7 and 8. How? Using an indicator function. Indicator function here is 0 when its condition is satisfied, and it becomes 1. Sorry, it's 1 if its condition is satisfied. Otherwise, it's 0. Right? Yes. So when OI is not equal to YI, this becomes 1, and I have this term, exactly how I had it in the accolade, right? When the condition is not satisfied, meaning that when OI is equal to YI, the indicator function is 0, therefore the update term goes away. Agreed? Okay. So we could restate them using indicator function. Now let's prove. Let's prove. So we have 2 proofs at least for perceptron used with the signum activation function. Proof 1. Consider this. Right? What was that? Yeah, we had this. Okay. When the output OI and the target label YI have labels +1 or -1, do you agree? Here. Then what happens? We have 4 cases. Do you agree? Either both are 1, or one of them is 1 and the other one -1. One of them is -1, the other one is 1, or both are -1. Let's consider all of the cases. When both are 1, this becomes 0. Okay, this term. By the way, here, what am I doing? I'm starting from this. This was for binary, right? And I'm deriving this formula for when I'm using sign, right? When both are equal to each other, then this becomes 0. Also, this becomes 0, right? Okay. When one of them is 1 and the other one is -1, let's consider yi equals 1 and oi equals -1. Then this becomes, I replace yi with 1 and oi with -1. Then 1 minus -1 becomes 2, right? I have 2 eta xij. Can I say it is equal to 2 eta yi xij? Because yi is 1. Now let's consider the other way around. So when yi is -1 and y is 1, I will end up with -2 eta xij. Then can I say it is 2 eta yi xij? So because yi is -1. Exactly the same trick that I explained. For this trick, we are saying that let's consider -1 and 1. So we unified these 2 cases, right? And this is exactly what we had in the formula for this. Now it answers your question why we have 2 here, right? Okay. This was proof 1. Proof 2, using gradient descent. This proof is very interesting, inspired by teaching of Professor Ali Qudsi. Okay, what is this? We can actually see the update formula of the perceptron as a gradient descent algorithm. Let's see that. So we want to find a linear decision boundary, okay? Because perceptron is giving us it's a linear classifier, okay? It gives us a linear decision boundary, where one class falls in one side and the other class falls on the other side. Exactly, right? This is a linear classifier. So assume my classes are linearly separable, then I can draw a line between them to separate them, right? The equation of a line for linear decision boundary is this, right? This is linear or affine decision boundary, right? W transpose X plus W0 equals 0. This is the equation of a line, right? Then X is d-dimensional and W is d-dimensional. Do you agree? By the way, W here, when it was a scalar, it was Wx in high school, Wx plus W. W was showing the slope, right? Here, when it is multiple dimensions, W is a normal vector. So when also you can see the normal vector as kind of a slope, right? Because when you change the slope of this line or this hyperplane, the normal vector also changes. So this is the normal vector. Why is it called normal? Because it's orthogonal to the line. Okay. And yeah, normal vector of the line, and W0 is the bias, also called intercept of the line. Now consider any 2 points, x1 and x2, on the decision boundary. Any 2 points. Okay. Like this in this figure, consider it is, assume it is in 2D, and therefore this becomes a line. By the way, in 3D it becomes a plane. In 4D it becomes a hyperplane, right? So here I have 2 points in this line, x1 and x2. Therefore, both of them satisfy the equation of line, right? They both satisfy equation 9. So I can say W transpose x1 plus W0 equals 0, and W transpose x2 plus W0 equals 0. Agreed? Okay. According to these two, they are equal to each other. W transpose x1 plus W0 equals W transpose x2 plus W0. the W zeros can be cancelled, right, from the sides. Then I bring W transpose X to the other side, and then I left factor out W transpose, right? So I will have W transpose X1 minus X2 equals 0. When I say X transpose Y equals 0, two vectors, their inner product is 0, what do I mean? They're perpendicular to each other. Therefore, yeah, exactly. W is perpendicular to X1 minus X2. This also is a proof of why W is a normal vector. So what is X1 minus X2? The vector connecting X2 to X1. This is exactly this vector. And this is W. We just proved that W is also a normal vector, right? Now consider a point x0 on the decision boundary. Consider a point like this, right? And a point x on one of the sides of the decision boundary, such as this. Agree? Okay. Then, as the x0 is on the line, it satisfies the equation of the line. Therefore, W transpose x0 plus W0 equals 0. I can rearrange the terms to get W0 equals minus W transpose x0. Agreed? Okay. Now assume the normal vector W is normalized. What do I mean? It has unit length. Okay. Then the distance of point X from the decision boundary, what is this distance? This, the distance of this part, right? This is the distance, right? Because the distance of this point from here, you can see it here, right? This distance I did D. Don't confuse it with the dimensionality. Here D means distance, okay? Is what? Is W transpose X minus X0. Why? According to simple linear algebra or geometry. So this is, consider this. What is this? This is X minus X0. So what is the vector X minus X0? Vector connecting X0 to X. This vector, right? And what is this? This is exactly the inner product of W transpose X minus, so this vector, inner product by this vector, but you have to normalize this vector, right? You have to normalize this vector to get this. Whenever you learn about inner product, they show you this figure. They say the inner product, you can see it as a length of projection of one vector to the other one, but one of them must be normalized, exactly. So I have W transpose over its length, L2 norm. However, I assumed that W is normalized. Therefore, its L2 norm is 1. Therefore, I can assume this distance is W transpose X minus X0. Clear so far? By the way, whenever you don't understand anything, just ask me, interrupt me, okay? Let it be crystal clear for you. Now, I multiply these to the terms. I have W transpose X minus W transpose X0, right? Then what happens? I can replace, what is this? According to equation 10, this is W0, right? Do you agree? Okay, so D is W transpose plus W transpose X plus W0. We just proved that, right? The distance, however, must be non-negative, right? This is one of the properties of distance, right? Therefore, but this might be negative. Therefore, I need to have absolute values. So distance is the absolute value of this, right? Agree? Okay. Now we use that technique that I told you. So I have +1, -1 as the labels. So rather, absolute value, by the way, whenever I see absolute value in optimization, I get a square. Why? Absolute value is not a smooth. Have you seen the function absolute value? This is absolute value, right? Do you agree? This is absolute. In the origin, it's not differentiable. It's not a smooth. So you should get scared, right? Therefore, this is a pain in the neck. How do we get rid of that? Using the technique that I told you. So Whenever I know that, whenever W is 1 in the class +1, its distance is positive. Why? Because it's above the line. Whenever it's in the class -1, its distance is negative because it's below the line. As a result, multiplication of the label by this distance is always positive, always non-negative, I mean, right? Therefore, I can consider this as the distance. Interestingly, equation 13, this one is a smooth. Although equation 13 is equivalent to this absolute value equation, absolute value of equation 11, but this absolute value is non-smooth. But equation 13 is a smooth. Very interesting. Okay. Now, a possible cost function. We can have various cost functions. We want to minimize some cost function, right? In gradient descent. So it can be number of misclassified data points, right? Let's minimize a number of misclassified data points. But is it easy? When you say number of something, what is it, discrete or continuous? It's discrete. In optimization in mathematics, whenever you hear the word discrete, you should get a skirt. Discrete optimization is much harder than continuous optimization. Okay, it's very hard. That's why usually in discrete optimization, they try to relax the problem to a continuous optimization. Have you heard of integer linear programming? Okay, there is a technique named I think it was called branch and bound or tree, using the tree. So they say, let's have I have a discrete linear programming. So it's a linear programming problem. My variables are discrete. Let's relax it and assume the variables are continuous. I solve it. Then I have two cases. Either I'm below that or above that. Then I solve these. Then they become again two cases. So it becomes a tree. So at every point in the tree, they relax the problem to a continuous problem. You see, this is how much this is hard. For solving a discrete optimization problem, you have to solve maybe 100 continuous problems, right? Okay. So
Why discrete optimization is harder?
Why is discrete optimization harder? Because in continuous optimization problem, when you have the cost, you can move along the cost. You can go with whatever step you want. In discrete optimization, you have to jump between the points. It's very hard. Jumping is hard. So it is hard to just optimize, right? So by the way, discrete optimization is also related to combinatorics. One of the hardest parts. If you have done any Olympiad of mathematics, combinatorics is hard, right? Okay, so let's optimize the distance as rather than optimizing the number of misclassified points. Let's have another cost, which is easier. Let's optimize the distance as a cost. So if a point is misclassified, let's minimize the distance of misclassified points. Right? Approach 1. We want to maximize the distance of points from the decision boundary. Its idea is similar to support vector machines. The idea is in SVM is also this. It says maximize the distance of points from the decision boundary. So we use gradient ascent for maximizing the distances of points from the decision boundary. Gradient ascent is the opposite of gradient descent. For when you want to minimize something using first order derivative, it's gradient descent. But when you want to maximize something using first order derivative, it's gradient ascent, right? And it's not equivalent to SVM, what we are doing. Why? SVM maximizes the distance of only support vector. What is that? Let me add a page. So assume I have these points as the classes. Okay. Then the line between them, for example, is this. Which points from each of the classes are the closest to the line, decision boundary? This is a decision boundary. Which point, for example, from this class, this is the point, right? From this, maybe both of these, maybe almost equal length, right? These are called support vectors. Okay. SVM only considers the distances of the support vectors from the decision boundary and ignores the other ones. Hence, SVM is a sparse. It's only considered some of the points. Hence, its name is support vector machine, right? But in Perceptron here, we are optimizing the distances of all of the points from the decision boundary. That's why Perceptron is not equivalent to SVM. Actually, SVM is much better than Perceptron. Okay. So let's go back. And so here I have this. This was the distance, right? And I have the batch. So I sum over the batch. This is a distance. What should we do for optimization? This is the cost, the distance, right? Take derivative with respect to my optimization variables, which is, what are the optimization variables? W here, the weights, okay? And so what is the derivative of this with respect to W? It's linear with respect to W, right? So I have summation of this yi times xi. Agreed? Also, I have two optimization variables. One of them is vector W, and one of them is a scalar W0. So I take derivative with respect to W0 also. With respect to W0, this is also linear. It becomes only summation of yi. Right? Now we do the gradient ascent. W equals W plus, because it's gradient ascent, some learning rate, the gradient. This is gradient, right? Derivative. Also for the other one, I use this gradient. What are these? We just proved Perceptron. This is the update of Perceptron which we saw in the previous slides. Interesting, right? Okay. And interestingly, yeah, that's correct. Okay. Let's go to approach 2. Approach 2 is another approach. So we take the distances of misclassified data points as the cost function, right? What do I mean by misclassified? Assume in this case, if I have this here, if I have a circle here, this is misclassified, right? It has some distance, right? I want to minimize this distance because I want to push this circle to its own class. So it's ideally this distance becomes 0, okay, or negative. So here I have to minimize this distance, the distances of misclassified points, and according to equation 12, the distance in equation 13 is for correctly classified data points. What was 12 and 13? Let's see. According to this, right? What is this equation 13? D equals y times W transpose x plus W0. This is for correctly classified points, right? According to equation 12, we have when y is plus 1, this is greater than 0. This is correctly classified. When y is minus 1, this W transpose x plus W0 is negative. That's also correct, right? So the correct distance is y times W transpose x plus W0. So the incorrect ones becomes negative, right? Let me tell you with more detail. For incorrect, the equation 12 becomes this. When y is 1, W transpose x plus W0 is negative for incorrect classification. When y is minus 1, W transpose x plus W0 becomes positive, right? Therefore, the distance for incorrect classification becomes minus y W transpose x plus W0, so the distance becomes always positive, right? Okay. So I have these, and I have the summation over the batch. Therefore, this is the error, right? I can bring this minus out of the summation. Now I do gradient descent this time because I want to minimize the error. So these are the gradients with the minus because of this minus. If I put them in the gradient descent, they become exactly that formula, right? I think it's obvious this becomes the other one because gradient descent of minus function is equivalent to gradient ascent of the function, right? Is it clear now? We just proved that formula. Problems with Perceptron. Perceptron has problem. First off, various problems, we enumerate them here. It's just for binary classification. But one might say, okay, if we have multiple classes, then we can consider pairs of classes. Okay, that's. In 1969, Minsky and Papert published a book titled Perceptrons. Okay. Then after this, the interest in perceptron declined because they showed that perceptron has a lot of flaws. Okay. So they showed that perceptron can only solve linearly separable problems. Until then, whenever like Rosenblatt and others, they only were considering linearly separable classes. They weren't even thinking about what if the classes are like XOR. What is XOR? This is XOR, like X. These are non-linearly separable classes. You can't separate them using one line, right? Then in Minsky and Papert showed that perceptron can't solve the XOR classes. Okay, but they showed that it cannot classify XOR classes, which is a nonlinear classification problem. Therefore, researchers lost interest in perceptron. They understood that they haven't solved AI yet and artificial neural networks. Okay, researchers guessed that they should have multi-layer perceptrons. So how to tackle this problem of solving nonlinearly separable classes? Let's stack several linearly separable linear classifiers, linear perceptrons. Let's stack several. Maybe it becomes powerful, right? To be able to handle nonlinearly separable classes. They did not know how to train the multi-layer perceptrons. They didn't know that. Okay. Also, perceptron cannot generalize well. This is the other problem with perceptron. That because for linearly separable classes, assume even the classes are linearly separable. Still, what it finds might not be perfect. Why? Consider these two classes which are linearly separable. Whenever you run perceptron, you might end up with one of these lines, depending on the initial points, because you need to initialize the weights, right? Because this is iterative optimization, right? So you need to have initial. Depending on your initial solution, you will end up with different solutions. And maybe in all of these, one of them is perfect. One of them is very awful. Why? For example, consider this case. One perceptron might give you this. Is it good? Not at all. It's completely skewed, right? So it's close to one of the classes and very far from the other one. In other words, it is not generalizing well. Why? Consider this case. Then when I have a test point here, which is actually a cross class, then what happened? Perceptron says that this is circle, right? Although if it was here, it would say that this is correctly cross, right? So it cannot generalize to unseen data, to test data. Well, which decision boundary generalizes well? the decision boundary which is exactly between the two classes with the same distance from the two classes, right? This is the best generalization that we can have using a linear classifier. This is exactly the idea of SVM. So when Perceptron came and they saw these flaws, someone named Vapnik, who is a very great mathematician, said, let's find the best decision boundary, which is exactly between the two classes using optimization. And they called it support vector machines. Okay. So yeah, here it is. I'm showing you that Perceptron is not generalizing well. Because of this problem, two things were developed. First off, ADALINE in Stanford, which generalizes better. Okay. And support vector machines, SVM, which found the best decision boundary by optimization of the distances of the support vectors from the decision boundary. And I think you can guess what was the idea. What was the idea of SVM? Can you guess it? Yes, but how do they optimize it? Assume, let's go back to 60 years ago, 7 years ago. You were in the shoes of Vapnik. You wanted to design some optimization problem. You say, okay, I have some classes. Okay, assume I'm Vapnik. How can I find a line which is exactly between the two classes? Oh, yes, we should only consider these points. The other ones are not important. Okay. By the way, so let's call them support vectors, whatever. And these have some distances, right? The distance should be exactly equal. So this D should be equal to this D, right? But how can I make this D and the other D equal to each other? I'm designing the algorithm, right? How can I make the two Ds equal to each other? Assume this was a human, Jack. This was Jennifer. Okay, Jack and two humans. And this was the wall between them.
Minimize the difference between.
Minimize the difference between those two distances. Kind of right, yes. But I want to make an analogy for you to understand how SVM is working. Assume this is a wall and I have Jack and Jennifer. They are playing a game. They push the wall toward each other. Because if Jack is stronger than Jennifer and pushes this line toward Jennifer, it is better for Jack. Why? Because it generalizes better for Jack's class, right? But if Jennifer is stronger and pushes the wall toward Jack, it is better for Jennifer's class. It generalizes better for, but let's assume that both Jack and Jennifer are equally strong or equally weak. Then what happens? The wall stands exactly between them, right? This is the intuition behind SVM, okay? And then he worked on the mathematical optimization problem, which we will cover in a statistical machine learning course, not in this course. Okay. So, yeah, we said that. Okay, Ada, let's have a break and come back at 8:45. Okay. Thank you. Okay, before we continue, one of you guys mentioned about the fact that the population of classes now is 35. So it's above 30, and according to the rules, it can have TA. So I contacted the department. They said we should wait until maybe end of week 4 to see whether still there will be more than 30 students in the class, and then they will decide whether to add the TA or not. I agree that it's too late then, because I think, yeah, it means that after 1 month they will start to decide whether we'll have a TA or not. I don't know. So as a result, we can't change the outline currently, at least. If they add a TA, I might make a poll. I think assignment, yeah, I don't know. Whether only for assignment 2 or for both assignment 1 and 2, I will make a poll asking you whether you want those to be graded and considered as a part of your grade or not. Let's see what happens in the future. I don't know. Okay. But whatever decision I make about the grading, if they add it here, I will make a poll and ask you guys, and we will do according to the majority vote. Okay. So, by the way, another person also asked me a question about the regularization using L1 norm and L2 norm, which was in the video that I requested you to watch. I'll explain it briefly for them. But again, if you have any questions regarding that video, feel free to ask me. And also, I will go through the slides of that video very fast. And then I will go to the regularization of deep learning. But please watch that. And if you have any questions and ambiguity, feel free to ask. You can also ask in the Teams group, right? Okay. So let's continue. ADALINE. In 1960, Widrow and his student Huff at Stanford University proposed a method named ADALINE for adjusting weights. In 1960, articles claimed that robots can think. Okay, again, they got excited. It has more generalization compared to Perceptron. Okay, ADALINE, what does it do? It minimizes least mean squares error. So least mean squares error, what does it mean? It's minimization of mean squared error. So least means minimum, minimize. Mean squared error, you can see that, yeah, mean squared error, I think it's obvious. Okay. Using gradient descent. Okay. So you can see that gradient descent was getting popular in machine learning gradually. This training method is referred to as LMS algorithm, short for least mean squares error, or Widrow half learning rule. Okay. So this is the structure of ADALINE. One big difference compared to Perceptron is what?
The output is independent of the.
Yeah, exactly. The output comes from before the activation function rather than after activation function, right? That's one thing. Another difference is what? The learning part, exactly. Rather than Hagen learning, we have LMS learning, right? Okay. So in ADALINE, the target label is compared with the output before activation function. This is while Perceptron compares the target label with the output after activation function. Now I think you understand why ADALINE is generalizes better than Perceptron. Why? Because ADALINE compares because here this is the output is float, right? Float value. Here it becomes binary, right? Perceptron makes the output crisp, the binary, and then compares with the target. But ADALINE compares the target with the float, a continuous value of the output, right? Okay, so I have this summation. I don't feed it to the activation function right now for this, right? By the way, for test, finally, for whether saying this point is in the class 1 or class 2, 0, 1, I have the activation function, but I don't use it for training. Okay, you get it? So I have this, and I compare it with the yi, and what is this? So this is the error. I square it, and then I sum over the batch. This is mean squared error, right? I have also 1/2 here. Why? Because I have a square here. When I take derivative, it becomes 2 something. So x squared becomes 2x, for example. That 2 is a pain in the neck. I want to get rid of that. So I have 1/2 here, right? That's fine. And b is the batch size. xi is the ith point, and yi is its target label. Here I haven't divided by b to become mean. Doesn't matter in cost. If you multiply the cost by some scalar, does it matter? If you minimize f of x or minimize 1/3 times f of x, you're still you will get the same solution. Okay. Okay. Hi. So we had the LMS error. This is what we had, right? LMS error. Now we want to do gradient descent, right? So derivative of error with respect to wj. What does it become? Can you tell me? First off, it's chain rule. Okay, it's chain rule. Consider this whole thing to the power of 2. Its derivative becomes 2 itself, right? Because the whole thing here is a scalar, right? A scalar squared, its derivative becomes 2, that is scalar, right? So it becomes 2 times this. That 2 is cancelled with 1/2, right? So I will have this and this. Now let's go inside. We are doing chain rule. The derivative of this term inside with respect to wj, can you tell me what is it? This part is constant with respect to wj, right? This part is constant with respect to wj. Only this part is important, right? Summation of wj xij. But what is, so by the way, I have this minus behind that, minus summation of wj xij. Therefore, I have this minus here, right? Now let's consider summation of wj xij is derivative with respect to wj. What is it? xij. But where did the summation go? What? No. What? Exactly. You're right. Let me explain it. These are the techniques that you should learn. So when I say wj xij, j goes from 1 to d. What is it? It's actually w1 xi1 plus w2 xi2 until wd xid, right? When I say the derivative of this term, let's call it c. Derivative of c with respect to wj. You can see it, for example, as derivative of c with respect to w1 or w2 or w3, whatever. Consider derivative of c with respect to w1. What happens? All of the other terms are constant with respect to w1. Only one of the terms, and that's w1 xi1. Its derivative becomes xi1. Derivative of c with respect to w2 is xi2. Therefore, when you say derivative of c with respect to wj, it means that for a specific j. For a specific j, only the jth term remains, and the other terms are constant. So it becomes xij. Therefore, the summation goes away in derivative. Okay? As a result, I only have xij, not summation of xij. Agreed? Did you understand? Okay. So I do this for all j. For all j from 1 to d. I can also do this with respect to w0. What happens if I do that? Again, chain rule. But the term inside, only this term is important. The other terms are constant. And the derivative of this with respect to w0 is 1, but I have a minus here, which comes here. right? Now I use these in the gradient descent. So this is gradient descent, right? Wj is Wj minus eta. Eta is the learning rate times the gradient or derivative. By the way, we should note that if we put this derivative here, this minus and this minus cancel each other and they become positive. Okay, be careful about it. Okay. Let's go to ADALINE. So that was ADALINE. This is ADALINE. At the Stanford University, Withrow and his students stacked several ADALINE neurons. Do you remember I said they saw, especially for Perceptron, they saw that Perceptron can only handle linearly separable classes. For nonlinearly separable classes, they said probably we should stack several linear classifiers. Hopefully they become powerful to handle nonlinear classes. Similarly, they did the same for ADALINE. They stacked several ADALINE neurons to have nonlinear classification. They proposed ADALINE or many ADALINE or multiple ADALINEs, many ADALINEs, right? So we have several rules for ADALINE. ADALINE rule number 1. It was proposed in 1962. By the way, I don't go into the details of ADALINE. I think it's not that much important nowadays, but I'm introducing it to you. It was proposed in 1962 and could not adapt the weights of the hidden output layer. What do I mean by hidden? Hidden layers means the layers in between. Okay. So this is, for example, ADALINE. Consider this ADALINE. But hidden output layer means here. Okay. They didn't adapt the weights of this. So as you see, every neuron here is an ADALINE. Every neuron here, if you zoom, you will get this figure. Right? Okay. As you see, they weren't using Perceptron. Perceptron was their competitor, right? So nowadays, when you zoom, in a deep neural network, when you zoom to a neuron, you will get a perceptron. You will see a perceptron. But for ADALINE, when you zoom, you will see an ADALINE per neuron. Okay. ADALINE rule number 2, proposed in 1988, not too far away. It was close to us. Improved MR1, ADALINE rule 1, and to be able to also train the weights of the hidden output layer. So they added training that layer too, that output layer too. ADALINE rule 3, it was proposed in 1990 and changed signum activation function or sign activation function to sigmoid activation function. This is a big leap. Why? Because until now, until that time, output after activation function would become only binary, only 2 levels, either 0, 1 or -1 and 1. So it became discrete. Now they say, let's make the output float continuous, right? So maybe we can handle regression with that too, right? If you want to do classification, you can apply some threshold on it. Nowadays in neural networks, we do that. We say with some probability, this point belongs to some class. And then we use a threshold on that probability, right? So the ideas come from here. They said, let's use sigmoid to make a probability or a continuous value as the output. So it was a big leap. Maybe, because especially according to the time, maybe they were inspired by fuzzy logic. I believe they were inspired by fuzzy logic. What is fuzzy logic? So there was a professor in US named Lotfi Alizadeh. He said, rather than binary logic, 0 and 1, let's have a continuous range. As the example that I always say, when I say, are you well or not? You can say that I'm not well or I'm well. Or you can say I'm 70% well, right? So you can have a range, a float range. Then he proposed a logic and for continuous values, and he named it fuzzy logic. Okay, so especially at that time, fuzzy logic was very popular. So maybe they were inspired by fuzzy logic. Okay, so they changed it to sigmoid function for having float outputs rather than merely binary outputs. And I think it was in this paper, I guess, in 1990, they published a paper, a survey paper, or whatever they have done in Stanford in the last 30 years. So they said, let's celebrate the 30 years of trial on neural networks on ADALINE. Okay. Now let's go to logistic regression. You might be wondering, how is logistic regression related to neural network? I can tell you logistic regression is a neural network with one neuron. Okay. So logistic regression, first off, its name is misleading. So it's not for regression. It's a classifier. It's for classification. Why do we call it regression? Because as I said in preliminaries, you can see classification maybe as a special case of regression. You output some probability, then you using a threshold, you can say whether it's in class 1 or class 2, right? So the same idea here. We regress some continuous value, and then we decide which, based on that, using a threshold, we decide which class it is, right? So logistic regression is popular in biostatistics and bioinformatics, especially in, I think 10 years ago, in this, most of the papers which were using data analytics in biostatistics and bioinformatics and biology, they were mostly using logistic regression. Okay. Let X be d-dimensional data and Y be the class label. So as I said, it's classification, right? According to the Bayes rule, is that we have this probability of Y given X equals probability of X given Y times probability of Y over probability of X, right? This, we call it posterior. This, we call it likelihood. This, we call it prior on Y and prior on X. I think it's obvious, right? So what is posterior? It's root. It's posterior. It's a Latin word. So it means that it comes after, right? So it means that after seeing the data, what is the probability of my label? Okay. The likelihood is, the meaning means probability. So given the label in each class label, what is my probability? This is likelihood. In each class, what is my probability? We call it likelihood. What is prior? So I know it beforehand. I know the probability of labels beforehand. I know the probabilities of my data beforehand, prior. I think they came to mathematics from philosophy, especially at the time of Kant, or Kant also. They pronounce it in different ways. Kant, Immanuel Kant, what did he say? So we have a priori propositions and a posteriori propositions. Some things we know it without experiencing the world. Some things we know it by experiencing. Okay, this is in epistemology of Kant. If you are interested, you can Google it and take a look at that. Kant said that, explained that in his book, Critique of Pure Reasoning, I guess, yes. Okay, so anyway, that came, so mathematics borrowed that from philosophy. So in contrast to linear discriminant analysis, or LDA, logistic regression works on the posterior directly rather than working on likelihood and prior. So there are two approaches. I want to maximize, assume this Bayes rule, okay? I can either maximize this posterior or likelihood times the prior. So you can maximize either the left-hand side or the right-hand side, right? So LDA maximizes this right-hand side, but logistic regression maximizes the left-hand side. Okay, that's one difference between them. LDA, by the way, what is that? That's a linear classifier in a statistical machine learning, not related to this course. Okay. Okay, logistic regression, let's talk about, so it's a binary classifier where it assigns probability between 0 and 1 for belonging to one of the classes. So when I have binary classes, I can consider only one of the classes, and I say probably with probability 0.7, for example, it belongs to class 1. It means that with probability 0.3, it belongs to class 2, right? Because the probabilities need to sum to 1. Agreed? Okay. The logistic function. So in logistic regression, we use the logistic function. Hence the name logistic regression, because it uses a function named logistic function. Used in logistic regression, it was initially proposed in 1845. Okay. For modeling the population growth. Why is it important for population growth? This is, by the way, the logistic regression, logistic function. So it goes to 1, from 0 to 1. Why can it model the population growth? Initially, my population is close to 0. Assume we have some humans in some region. Initially, we have a few humans. Then they mate with each other. They will have offsprings, children, right? The population grows gradually. Then they use the resources. They eat. They use the hygiene and everything. They grow. They will have population explosion, right? But we reach some point where there is not enough resources for the humans, right? So the hygiene decreases, the amount of food decreases, right? Therefore, some people die. So it stagnates. That's why logistic function can model population growth. Okay. It was further improved in the 20th century. You can see this reference for a history of logistic regression. Okay. It considers the logistic regression, considers the classification problem as a regression problem where it regresses or predicts, right? The probability of belonging to a class, as I said. Okay. So what does it do? It first considers a linear regression beta transpose x plus beta 0. So when I say assume I want to design, whenever you want to learn an algorithm, assume you are the designer of the algorithm. Okay. So assume I want to design the linear, the logistic regression. I want to regress, right? The simplest way to regress is a linear regression. Let's start with the simplest. So let's use beta transpose x plus beta 0. This is a linear function, right? Whose parameters are beta and beta 0, right? Let's learn them. However, there is a problem. What is the problem? This line beta transpose x plus beta 0, does it have any bound? It can go from minus infinity to infinity, right? By sweeping x, beta transpose x plus beta 0 changes from minus infinity, because line goes from minus infinity to infinity, right? We have to bound it somehow. Why? Why do I need to bound it? Because I want it to become probability between 0 and 1. How can I bound beta transpose x plus beta 0 between 0 and 1? I can use exactly the logistic function, because it takes all range of x from minus infinity to infinity, and it maps it to between 0 and 1. Right? So, yeah, as I said, by the way, here, x, I'm adding 1 as one of the dimensions, an additional dimension to x. Why? To handle beta 0, to handle the bias. Therefore, I can absorb beta 0 in beta, so beta becomes d plus 1 dimensional, right? Didn't you understand that? So x is d-dimensional. Beta transpose x plus beta 0, beta is d-dimensional. But I can write it this as only beta transpose X if I consider this D plus 1 dimensional. And I assume that one of the dimensions like X0 is 1, right? We have to have bias. Why? Because what if my data has bias in it? When my data has bias in it, for me to predict that, my prediction should have the bias also, right? However, okay, as I said, we use logistic function. It is also called sigmoid function. The logistic function also called sigmoid. Okay, so assume we have two classes Y, therefore the labels are either 0 or 1. Logistic regression models the posterior using a logistic function. So what does it do? It works with posterior and says, let's model it using a logistic function. So I have this. E to the power of beta transpose X. Where did this power come from? This is exactly beta transpose X plus beta 0, where I absorb beta 0 inside beta. Okay? So this is linear regression. This power is linear regression, but it's not bounded. It's bounded between 0 and 1. Therefore, I put it in this logistic function. And this is, so for, I use this for the posterior of class 1. So the posterior of class 1 probability of Y equals 1 given the X is this. Therefore, the posterior of the other class is 1 minus the posterior of that class, right? Because the posteriors should sum to 1. I have two classes here. If you have 1 minus equation 21, you will get this. Right? Agreed? Okay. Now so beta is D or D plus 1 dimensional. I think this should be D plus 1. Okay. Now let's see the plots, the figures of these logistic functions. So this is sigmoid. Give me a second. This is a sigmoid function. Or logistic function. 1 over 1 plus e to the minus x. Forget these two equations for a second. Consider this sigmoid function. Its plot is this. Okay. Why? Let's analyze it. Limit x to minus infinity. What happens? E to the minus infinity becomes e to the infinity. E to the infinity is infinity. The denominator blows up. So the whole thing goes to 0. So the whole thing goes to 0. Limit x to infinity. E to the minus infinity becomes 0. Then the fraction becomes 1. So it goes to 1. All right? Now rather than x, I put minus beta transpose x. Do you agree that rather than x in the sigmoid function, I can put anything? I can put Benjamin. 1 over 1 plus e to the minus Benjamin, right? Rather than Benjamin, put minus beta transpose x. You will get this. Right? Exactly equation 21. Okay? And again, you can analyze it. Limit beta transpose x to infinity. This fraction becomes 0. Limit beta transpose x to minus infinity. This fraction becomes 1. And this function here, if you also limit beta transpose x to infinity and minus infinity, you will get this behavior. As you see, compare these two figures, these two plots. They are opposite of each other, as expected, because the probability when the probability of one of the classes goes up, the probability of the other class goes down, right? Because they should sum to 1. Okay. Now, logistic function can be seen as a neural network with one neuron, right? Let's see where the activation function is the sigmoid or logistic function. And actually here, the activation function is nonlinear, right? It's not binary. It's sigmoid. So I have, what is this part? Can you tell me? This is exactly linear regression. This is exactly beta transpose x or plus beta 0. Or if we absorb beta 0 into beta, it becomes beta transpose x, right? And this is a logistic function. That's exactly one neuron of neural network. Okay, you can see it. Okay. So now let's train logistic regression. We go to training. Consider n data points, x1 to xn, with their labels, y1 to yn. And the labels are scalar here, right? The points are d-dimensional. Assuming that they are independent and identically distributed, or IID. What do I mean? Assume that the points are from the same distribution, but they are independent from each other. Okay. Then the posterior over all of the data points is this. So consider only the ith point, Then this posterior probability of y given x, you can see whether there are two cases, whether the point belongs to class 0 or class 1, right? If it is in class 0, this is indicator function, right? Indicator function of y 0 equals 1, 0. Then my posterior becomes posterior of y equals 0 given it. When my point belongs to class 1, the posterior becomes posterior of class probability of y equals 1 given x, right? And I sum them because I have these two cases, right? Right? Why do I have this multiplication? Because this is the posterior for every point. And now what about all of the points? I can multiply these probabilities. Why? Because they are independent of each other. Okay. Now what happens? This plus is a pain in the neck. Okay. How? Let's use a trick to get rid of this plus. By the way, when you learn these algorithms, you are learning the techniques too, right? So when you want to design your own algorithm, you can use these techniques, right? Because these techniques are used a lot in different algorithms in machine learning. So this plus is hard. So what should we do? We can say here, yi is either 0 or 1. Actually, this time is good for me to be 0 and 1, not -1 and 1. Okay. Here in this case, I want it to be 0 and 1. So if I write it in this way, what happens? When yi equals 1, I will have this term to the power of 1, but this term goes away because this power becomes 0. Everything except 0 to the power of 0 becomes 1. So it becomes 1 multiplied by that, right? But when my yi is 0, this power becomes 1 and this power becomes 0, and we will get rid of this term in the multiplication. Do you get it? So I could, using a technique of powering, we could get rid of that plus. Now, what should we do? Let's substitute equations 21 and 22, which were the logistic functions for the classes. Okay. This is the posterior, right? Let's replace this posterior with its logistic function, and this posterior with its logistic function, right? Okay, let's continue. Okay. We usually in machine learning consider the log of the probability. Why? First off, we have multiplication like this right here. Multiplication is a pain in the neck. Summation is easier. How can we convert multiplication to summation? Log, using log. Because log of multiplication becomes summation of logs. All right. Another reason is that we usually use exponential distributions in machine learning, such as Gaussian distribution. The distributions which have exponential operator, exp, in them. The Neper number to the power of something, right? This Neper number is a pain in the neck. Want to get rid of that. What is the opposite operator of exponential operator? Logarithm. Okay. So that's why we usually use the logarithm of the probabilities. So we have this logarithm of beta. So by the way, usually they say L of beta as a log, as a probability, and a small case of beta as its logarithm. Doesn't matter. This is notation. So I have logarithm of this that I had in the previous slide. Again, logarithm of multiplication becomes summation of logarithms. Then I have logarithm of this times this. Again, I can write it as logarithm of this plus logarithm of this, right? Okay. Now, again, this is the power yi. I can bring it behind the logarithm. So it comes here. Also, this logarithm can be simplified because we know that according to these formulas, log of a over b is log of a minus log of b. Also, log of a times b is log of a plus log of b. High school calculus, right? So we have this. We simplify it here. Also, this comes behind the logarithm, right? Okay. Now what happens? By the way, we also have logarithm of 1 over a is minus logarithm of a. So what happens now? Let me think. Okay, so yeah, multiply the terms to this. So I have minus 1 this plus yi this. Agree? I'm multiplying these two terms to this. What about the rest? So this is repeated. This logarithm and this exponential operator cancel each other. Agree? Okay. Interestingly, these two are the same but with different signs, so they cancel each other. So it simplifies to this, right? Okay. So I have this, I'm repeating it, what we found. Then this is my log posterior, right? Log posterior. Of course, we want to maximize it. What do we do? Take derivative, but we can't find a closed form solution, so we solve it iteratively. We can't find. If you take derivative, set it to 0, you can't find a closed form solution. Okay, so you should maximize it either using first order optimization or second order optimization. Here, let's do it with the second order optimization. Okay, so we use Newton's method. Okay, so Newton's method can be used. Therefore, we need both first order derivative and second order derivative. So let's calculate the first order derivative or the gradient. What is that? Derivative of this log posterior with respect to beta. What is that? Derivative of this term with respect to beta. It's a linear. It's linear with respect to beta. So it becomes yi xi. What about this chain rule? We should use the derivative of logarithm. Formula of derivative of logarithm of some function becomes 1 over that function, right? So I have 1 over that. Also the derivative of inside with respect to beta. So this is constant, goes away. Derivative of e to the, again chain rule. So we have nested chain rules. Derivative of exponential operator becomes itself. And the derivative of the power is linear with respect to beta, right? It's highest school derivative, but for vectors. That's it. Okay. Now, so I have this. I bring it to the numerator, right? Interestingly, I have xi here, also here. So I can factor out xi, right? Here. Initially, it might be hard for you to do the matrix calculations, but when you practice it, it becomes very easy for you. Very easy. Okay. You need to do practice. And by the way, I'll not ask proofs in the exam. Don't worry. So it's transposed now. Oh, now, so this is the derivative, equation 26. Then what happens? I need to transpose that. There is a reason. Because the second order derivative becomes this. Partial squared this log posterior with respect to beta times with respect to beta transpose. In other words, so I should take derivative two times, right? First time, I take derivative with respect to beta transpose and then beta. Why? There is a reason behind that. When I take with respect to beta, it becomes d by 1, right? Because I'm taking derivative of a scalar with respect to a vector, becomes a vector, and it becomes d by 1 vector. Then I want to take derivative with respect to beta again. This becomes d by 1 too. So if I make it 1 by d, the whole thing becomes d by d. That's the reason I transpose it. Okay. Anyways, so when we transpose this is scalar. It's not affected. Only this is transposed. Okay. So again, I need to take derivative of the first order derivative again for the Hessian, right? For the second order derivative. So what is the derivative of the first term is constant with respect to beta, goes away. This is a scalar multiplied by something, so it's not important. Now consider this. So I have only derivative of this term, right? Do you agree? Okay. Now for calculating this derivative, let's define probability of xi given beta. I define this function as this. This is my definition. Okay. So simply, I replace this with my definition. It is, I have this derivative. And I bring this negative outside of the summation. Okay. Therefore, we need to calculate this derivative. Let's calculate it. So this derivative, what is that? It's a fraction. What is the formula for derivative of a fraction in high school? uv minus vu over v squared, right? So derivative of, in other words, derivative of numerator is this. Times the denominator minus derivative numerator itself times derivative of denominator. Okay. And the denominator is a square. I'm using the formula of derivative of fraction. Now what happens? I have e to the power of beta transpose xi in here, well, in both terms. I left factor it out. So I will have these terms. Interestingly, these two cancel each other. Right? Therefore, I will end up with this. Agreed? By the way, I also write factored out xi. Okay. So I can write this term as multiplication of 3 terms. Agreed? Interestingly, the first term is this, what I defined, probability of xi given beta. And the second term is 1 minus what I defined. And then xi. Agreed? So let's put this derivative back in my equation 28. If I do that, I will have equation 29. Okay? Again, by the way, in my courses, you should be patient with math. You shouldn't get frustrated. Right? This is the only prerequisite. Okay? You need to enjoy mathematics. And you also shouldn't be worried at the same time, because you know that you will not be questioned. You will not have any question on proofs in exam. So with peace of mind, we try to understand. Okay. it is possible to write the Newton's method in matrix form, right? We can write it in matrix form. So let's define this. So I have X, okay? So I put X's, I have n data points, right? Column-wise, I stack them column-wise, but also I have one for bias to each of them, right? Therefore, the matrix X becomes D plus 1 with D plus 1 rows and n columns. Agree? Okay. I also define, this means definition in computer science. Okay. I'm also define W to be this, a diagonal matrix whose diagonal elements are this. Okay. So the ith element in the ith element in this matrix is this. Okay. I'll also have the vector of labels, which is n-dimensional. Also, I put these logistic functions as a vector because I have n of them, and I define it to be P, vector P. Okay. Now consider equations 26 and 29. So in other words, consider the first order derivative and second order derivative. Let's consider the first order derivative. Do you remember this? Equation 26 or here, doesn't matter. Okay, 26. Here, we should go back and forth. Sorry about that. So y minus px. Okay, give me a second. Okay, y minus px. Okay. Here I have y. What was this? The elements of p. Also have the elements of the x here. Okay, so here, consider this. Y minus p. I had xi's on the right hand side, but when I make it matrix form, I need to bring all of the x's stacked column wise to the left hand side. Why? For the dimensionality of matrices to match in matrix multiplication. Okay. So I have, this is exactly the first order derivative in matrix form. Agreed? Now let's see the second order derivative in matrix form. I need to go back and forth. See that? So we should get minus xw x transpose kind of, and where w is this? P xi given beta times 1 minus p xi given beta. Exactly here. This is the diagonal elements of w. I have, interestingly, see here, I have xi here and xi transpose here. In matrix form, that term becomes in between w, so I have x transpose. Agreed? And this minus came because of this minus. Okay. So what is this? The formula for Newton's method, but for maximization, because we want to maximize it. Here we have plus. If it was for Newton's method for minimization, we had to add minus here. We want to maximize the log posterior, right? Now let's put these two inside this formula. I will have this with minus. Why? This minus is not because of Newton's method. It's because of the second order derivative here. Minus here. Okay? So if I use this, do it iteratively, I convert to the solution of logistic regression. My betas were the unknowns, right? Now in test phase, what do? I get an x, I feed it to the posterior logistic functions that I have. Each class doesn't matter. Assume I consider, give me a second. Assume I consider this posterior, equation 21, in the test phase. I give x, so I already learned my beta, right? Now x comes, I've put it in this equation. Beta transpose x becomes a scalar. E to the power of beta transpose x is a scalar. Denominator is also a scalar. It gives me some number between 0 and 1. If this number is greater than half, then I say its class is 1. If this number is less than half, I say it belongs to class 0.
What if non-ag?
Not,
Your model is based on axis I, right?
yeah.
When you're testing, your test data is.
So the question is, what if my test data is not IID? First off, we assumed IID for training. Agreed. So IID was important for training, but maybe for test phase it needs to be also. So maybe if the test data point is not an IID, then it violates the assumption that we made in training. Therefore, its prediction is not much accurate. Because we have to satisfy our assumptions in the algorithm, right? Okay. So where are we? Okay. Yeah, this is in the test phase that I explained to you. We put it in the posterior of one of the classes to see its value. Just comparison to LDA, so logistic regression estimates D+1 parameters in beta, okay? Right? Because beta was D+1 dimensional. Agreed? But LDA estimates more parameters. I don't go into the details of this in this course because you don't know what LDA is in this course. But if we can calculate the number of parameters which we learn in LDA, it becomes D squared plus 2D plus 2, okay? D is the dimensionality of data. Compare this with D+1. Logistic regression has much less number of parameters to learn. Also, LDA has a big flaw. It assumes that the distribution of each class is Gaussian. Okay, but did we make such assumption in logistic regression? No, we don't care about the distribution of classes, right? Logistic regression does not assume about the distribution of data. Okay, let's talk about other history of neural network. So this is a very cool part. Let's see this. In 1969, Arthur E. Bryson and Yu Chi Ho described backpropagation as a multi-stage dynamic system optimization method. Okay. You can see the references also. Starting 1969, people started inventing and reinventing backpropagation algorithm for training multi-layer perceptron. So we know multi-layer perceptron is a stack of perceptron neurons, right? So at that time, I think, I don't remember the date of ADALINE, but I'm not sure whether ADALINE has yet started or not. So, but I'm sure that perceptron was there at that time. So people said, do you remember I said the book Perceptrons showed that one perceptron can't handle nonlinearly separable classes. So people try to stack several perceptrons and they try to train them, and they were inventing different algorithms for backpropagation. Okay, so they said let's use gradient descent for optimization. And why do we say reinventing? At that time, we didn't have archive and these things. People were not updated that much. Maybe some scientist somewhere invented that, another scientist somewhere invented that again. Okay. In 1972, Stephen Grossberg proposed networks capable of learning XOR functions, because XOR function was a representative for nonlinear classification. Okay. In 1986, the main and successful backpropagation algorithm, which is used nowadays, was proposed by David E. Rumelhart and Jeffrey E. Hinton and Ronald J. Williams. The most famous between these is the Hinton. You know Hinton, right? He was in the University of Toronto, and he retired several years ago, I guess. He also worked in Google. So in 1980s, by the way, you know Graham Taylor here, right? Do you know? He's a professor in the School of Engineering and Computer Science department here. He was the student, PhD student of Geoffrey Hinton. Okay, so in 1980s, it was successful era of neural networks. Okay, then kernel support vector machines resulted in the winter of neural networks in the last years of previous century until around 2006. So this is the cool part. So backpropagation was proposed. Then people saw that it is very strong. It can work very well, right? Then at around that time, SVM was proposed. SVM, support vector machine. People also got interested in SVM. People who liked math more, they got more interested in SVM because SVM is more theoretical, right, than neural network. So people who loved math, they tended to SVM. Okay, gradually, neural network got more interest. Why? Because neural networks could handle big data. SVM can't. Also, because SVM in its optimization, it uses interior point method. Interior point method is a bit slow for optimization. Also, SVM is linear classifier, but neural network multi-layer perceptron is a non-linear classifier. So neural network was winning, but Vapnik said not too soon. Vapnik said, let's make SVM non-linear. How? So there are two ways to handle nonlinearity in machine learning. Okay. Either you design a nonlinear algorithm, okay, or you transform your data, your nonlinear data. Hopefully, it becomes linear. Okay, and then you apply the linear algorithm on that. The second approach, which I said, transforming data, is called kernel methods, kernelization. So what does kernelization do in machine learning? It says, let's transform data from this space to another space. They usually call it Hilbert space. Doesn't matter, to some other space. Doing some map on this data to another space. Hopefully in that space, the classes become linearly separable. And then I use the linear classifier on that. So kernel SVM was proposed in around in 1990s, something like that. And Vapnik's group did that because they wanted to win back the competition against neural networks, right? To win back. So what did they do? They said, let's use kernel SVM to transform data so it becomes linearly separable. Then I apply linear SVM on that, right? So kind of kernel SVM was winning again against neural networks. Neural networks also face another problem. They couldn't make it deep. So they had, for example, 2 layers or 3 layers. But when they added layers and made it 10 layers or more number of layers, they had an issue and the issue was gradient vanishing or gradient explosion. The idea is simple. So in backpropagation, as I said, backpropagation is nothing but gradient descent and chain rule, right? In chain rule, you have multiplication of probabilities to each other, right? What if all of my probabilities are small? The multiplication becomes too small. What if my probabilities are high, large? The multiplication becomes too high. So either my gradients, the multiplication of probabilities, vanish to 0, or they explode to infinity. Okay, so I have gradient vanishing or gradient explosion when I have too many layers, because the more layers I have, the more multiplication of gradients I have. Okay, so that's a problem. They couldn't make multi-layer perceptron deep. Therefore, kernel SVM was getting better and better. But neural networks said not so soon to kernel SVM. There was a problem with kernel SVM. And what was that? What was the problem with kernel SVM? Yeah, exactly. Hard to form the transformation. So at least two problems with the transformation. First off, which transformation? I have several choices. So in other words, I have several kernel functions. I have RBF kernel. I have several choices. In philosophy, they say when human in existential philosophy, they say one of the problems of human, one of the existential problems of human is freedom. When you have freedom, you have responsibility. Okay, so people sometimes are afraid of freedom. Okay, so when you give freedom to the user, when you give too many hyperparameters to the user, this is a flaw of your algorithm. Okay, you shouldn't give too much freedom to the user. Your algorithm should decide itself. Okay, that's one problem with the kernel SVM. Another problem is that for calculation of kernel-made functions, when the data becomes big data, when the number of data points become big, it is hard to calculate because your kernel matrix is n by n, where n is the number of points. Okay, so the kernel matrix becomes too big. It may not even fit in the memory, especially the memory of computers at that time, 1990s, right? So we have also a space issue. We have time complexity issue. So kernel SVM cannot handle big data, although neural networks can handle big data because they are iterative and batch-wise. But neural networks couldn't become deep. So each of them has some flaw. Agree? Okay. So it went on and on until in the year 2006, Hinton, just give me a few, 2 or 3 more minutes and let me say this because the history is very interesting. So in the year 2006, Hinton proposed a famous paper in, I think, Science. Science and Nature are two important journals in the history of science, right? So in Science said, let's win back the neural networks against kernel SVM. How did he do that? He thought of one algorithm which he had proposed in 1983. Okay, he thought back. So Hinton had proposed Boltzmann machine and restricted Boltzmann machine, or RBM in short, in 1983 and 1985. Okay, so what is Boltzmann machine? Well, you have several neurons like this, or several units, whatever you call it. Also several units like this. And the units are connected to each other. Okay. These units also are connected to each other. So, right, like this. Then you can consider some energy, the energy concept in physics. So it's a physical system. Okay. Energy in this layer, also some energy in this layer. You can copy the energy from one layer to another layer, but this copying is not easy. Why? Because the number of neurons in these two layers is not equal. If the number of neurons is equal, you can exactly copy that to the next layer. But when the number of neurons is different, you are kind of, for example, going from more neurons to lower number of neurons, you should kind of do dimensionality reduction to preserve the information or the energy and lose as less information as you can. Okay, so they proposed Boltzmann machine for doing that. Okay, and this is related to probabilistic machine learning, by the way. Hinton said, by the way, around the year 2006, every layer of neural network, multi-layer perceptron neural network, is a Boltzmann machine. But there is a problem. In Boltzmann machine, I have connections between the neurons of the same layer too. Let me remove these connections. In other words, let me restrict this Boltzmann machine. So I call it restricted Boltzmann machine. I remove the connections between the neurons within each layer. And interestingly, every layer of neural network, multi-layer perceptron, is a restricted Boltzmann machine. Then in 2006, he proposed a paper, a method called deep belief network. Okay, What did he say? He said, let me consider every layer of neural network as an RBM. So a neural network is a stack of RBMs. I do that. I train that using RBM training, using probabilistic machine learning. Then I initialize backpropagation by the solution of RBMs rather than random solution. In practice, they saw that if rather than random initialization, if I use the initialization by RBM networks, you can make it deep. You can make the network deep. So the problem of gradient vanishing and these things were solved in the year 2006. Neural networks won the competition back against kernel SVM. Because before that, we had winter of neural networks, right? The winter ended. However, I'll finish it very soon. However, in the year 2012, 11, 12, something like that, what happened? Hinton and his lab, also Benjo and his lab, and some others. Benjo is a famous professor in AI in Montreal. Okay, so he was a student of Hinton himself. So these groups proposed two regularization techniques, which we will cover in this course, named dropout and also ReLU activation function. Okay, using these two techniques, they found out in practice that even if you initialize randomly, you can make it deep. So you don't need RBM training anymore. Okay, so they put RBM training aside. Nowadays, that's why in deep learning we don't use RBM. We initialize them randomly because we are using regularization techniques. Otherwise, we couldn't make it deep. Okay, so yeah, as I said, if we consider the network as a stack of RBM networks, they called it deep belief networks. Why? Because these energies are also called belief. Okay, the probabilistic belief. Yeah, I think and just after that, so ReLU was proposed in 2011, dropout in 2014, and after that in Stanford University. In around 2012 and afterwards a bit, people found out that deep networks are very useful for different tasks, specifically for the computer vision and natural language processing. For computer vision and image processing and these things, Fei Li at the Stanford University showed that, and her students, who's currently, I think, at Google. And for natural language processing, who showed that? LeCun, Jan LeCun, I guess. Yes, Jan LeCun. He's in New York University. He's also one of the managers of AI in Meta or Facebook. Okay, and nowadays I think you understand why, especially until years ago, Google was the god of computer vision in industry, funded by Stanford and California and these things. Meta was the god of natural language processing and text processing because of LeCun and his group, right? So they found out, Google and Meta, they found out that deep learning is very useful for different tasks. So this was a brief history of neural networks. Just for more information on early history of artificial neural networks, especially perceptron, ADALINE, and these things, you can see this book, Fundamentals of Neural Networks, Architectures, Algorithms, and Applications. Also, some slides of this slide deck are inspired by teachings of Professor Ali Qudsi, Professor Fakhri Karay, and Professor Saeed Bagheri Shoraki. So these are the references. Yeah, okay. Thank you very much. Thank you. Thank you. Thank you.